In this video we're going to look at ALRT, aggregate LRT, which is basically a user interface for running and aggregating a number of individual LRT models. So I'm going to start by looking at three just standard LRT models that I've created for three separate PLC datasets, and then we're going to combine these in ALRT and run the forecast. So the first one is in this triangle group called DJ-CAL, C-A-L, Commercial Auto Liability, and I have something called Smooth 1 here, which is my previously created LRT model. Now if you look at the selections table here, you can see that the final selection, these numbers here, precisely duplicate the numbers in the row above it, which is the three parameter smoothing. So I can tell that this final selection was created by, at some point I double-clicked here and copied the three parameter smoothing numbers into the final selection, and the three parameter smoothing numbers themselves came from this row here, average of the last four, and I know that because of the agreement in color. They both have this shocking pink color. The to-ultimate number here was automatically created by the three parameter smoothing, and it was created on the basis of the ultimate being 14 periods. This means that it's 14 periods overall, including the periods in the original data. So the original data here is 1, 2, 3, 4, 5, 6, 7, 8, 9. So an extra 5 periods forward in development are taken to represent the ultimate. The ratios for each of those is computed interpolated using the three parameter formula. They're then multiplied together, and that produces this 14 period ratio. So that's the first triangle group. The next one is this one, CMP, and again with PLC I have something called Smooth 11. So in this case, again I've used three parameter smoothing. The to-ultimate is computed using 11 periods, so that's just 2 periods after the end of the reported data. The original ratios themselves that were smoothed come from this row here, the maximum ratios. They're this sort of jade green color, and you can also see that the starting numbers are almost exactly the same. Of course, the three parameter smoothing will even alter the first number as well. So that's that model, and the third one comes from here. That's also PLC. This is a two parameter smoothing model, in which again the original ratios come from this row, as I can tell by the color, and their arithmetical averages. And the ultimate is 14 periods. So there are my three LRT models. So now I'm going to go into my composite data set, composite triangle group. This composite triangle group was created using all of the DJ triangle groups. So I have access to all of them, but what I'm interested in is creating a composite cumulative data set which has the particular three PLCs that I'm interested in. Now I can use these buttons here to sort this group here, and hopefully I'll find the three that I'm interested in fairly close together. And what do you know, I do. Here they are. Now in order to put these into a composite data set, I need to first have named that composite data set. So let me create one, I'll call it CCHPL. Just highlight that. Now the highlighting that I did previously actually still exists, so all I've got to do is drag these three up, and they now are collected together in this cumulative composite dataset, CCHPL. So when I go now to the Models tab, under Cumulative I have my new cumulative dataset. There are no models because the Composite button is down. If I click the Related button, I get these three models, the models we looked at before. I can now open these in ALRT, and there they are. Exactly as before. If I want to begin or start play with the models, I can do it within each of these tabs. Each of the tabs in ALRT is a complete instance of LRT. So anything you can do in LRT, you can do in ALRT. There is in fact no need to have already created the models in LRT. You could just begin with an empty model, as it were, of the for the datasets in ALRT. What you'll get are the standard chain ladder, which is the default model, and then you can mix and match and put your different ratios in as you wish under each of the individual tabs before running the forecast. And that includes changing the numbers here for the size of the slice that's taken for the last n periods, calendar periods for the averages, or the distance out in the to ultimate, which is used in computing the to ultimate ratio using the smoothing formula. So that's individually chosen for each of the data sets there. So now I run the forecast, and again when I run the forecast I get an individual interface for each of the data sets for the inflation and discount factors, and I can enter any numbers that I wish in those tables. I won't put any numbers in this case. So after a few moments the forecast comes up. Here I've got an aggregate forecast which sums up everything in the individual tables, and I also have the individual forecasts, outstanding, ultimate, and so on. Each of the individual forecasts has its own individual Bornholder-Ferguson expected loss ratio page. The aggregate doesn't have an aggregate of the Bornholder-Ferguson. However, if you wish to do that, you can do that via the report. Now in this case, each of the individual forecasts was made from a paid loss. So we have the outstanding, we have the to ultimate, and we have the ultimate. We also have, in the summary, we have the calendar year summary. Now it's also possible in ALRT to mix together, to create a composite data set that mixes together paid losses and incurred losses, or mixes together any other kind of cumulative data set. So let's go back here and create a new composite data set that will combine an incurred loss with a cumulative, with a paid loss. And let's see what happens to the forecast in this case. So I'm going to create a new one using those same CCH, but this time I'll make one of them, some of them, first two I'll make paid losses, and the third one, CMP, I'll make an incurred loss. Where is it? Yeah, there it is. So now my composite cumulative data set contains two paid losses and one incurred loss. Now notice this incurred loss has an associated CRE triangle. This will matter a lot in terms of the forecast. So now let's go over to models, and you can see here that when I click on this model here, I've still got the related tab down, related button down. I only have pre-prepared models for the two paid loss data sets. There is no pre-prepared model for the incurred loss. So when I run ALRT here, the incurred loss data set will end up with the default model, which is the standard chain ladder volume weighted averages. So let me create a model here, and I'll create it by using 3-parameter smoothing here, and then I might do, just to be a bit fancy, I'll create a 2-parameter smooth model here, and then the last 3 ratios in the selection I'll take from the 2-parameter. And the first 5. I'm double clicking here and taking from the 3 parameters. So I've got a mixed one where I start out smoothing by the 3 parameters, then I move into these parameters smoothed by the 2 parameter. So, it's whatever I happen to choose. So this is my favorite model, and I can even name this as mixed smoothing, let's say. So now what happens when I run my forecast? Well, here you can see something funny is going on. This table contains a lot of blanks. And when you go to the individual tab for the incurred loss data set here, we can see that everything looks the same here. We have outstanding to ultimate. The reason we have outstanding here instead of ultimate minus incurred to date is because we had an associated CRE, which means we're able to calculate the paid to date. And so using the ultimate as worked out from the model and the paid to date, we're able to calculate the outstanding. So in the case of an incurred loss, that the existence of this column as an outstanding column depends on availability of the paid to date data and is calculated by a slightly more roundabout way, you could say, than in the case where the triangle is paid losses. Now, where this is an incurred loss triangle, all of the numbers that appear here, well, these are incremental incurred losses. These are the actual cumulative incurred losses. So these numbers aren't really the same as the numbers that occur in the paid loss table. They can't strictly be compared. Incremental incurred losses, these are the increments by which the incurred loss numbers were updated each year. So that's why when I look at the aggregate table here, I have asterisks in these entries here, because it's underlining to us that we can't actually add up paid losses and incremental incurred losses. However, we can add up this table. We can add up the outstandings because the models in all 3 cases produce outstandings. When I look at the summaries, I have the summary, the sum of the outstandings and the sum of the ultimates. I don't have a calendar year table at all, because the calendar year table, in the case of the incurred loss, the name of those numbers that you get when you add up the calendar years along the diagonals in the incurred loss forecast, we call those mean incrementals. They're not actual predictions of what you're going to pay in those calendar years. They're just the mean of the sum of the incrementals for those calendar years, a number which you can interpret as you would like. However, it's not the same as the number that you get in the paid loss forecast. So in the aggregate, that sum doesn't appear. Now, if my incurred loss, let's just do one more of these. What if I went back, and I'll have to create this with CMP. I'll create a new, here my ILC under CMP is associated with the CRE, so I'm going to create a new ILC, and this time it's called ILC1, and this time it'll have no association. So now, if I go back here and I create a new composite cumulative data set, which I will call CCHPLIL1, and in this case, what I will do is begin as before with the which was the one? It's a Cal, so it had the so these two paid losses will go in, and the incurred loss that will go in will now be this one here, and this is the one without an association. So now when I run this, I have here I've got LRT models. I have two of them for HOFO. I'll use those two. But I don't have a LRT model for the incurred loss component, so again that will revert to the default. This time let me just stay with the default. I'll run the forecast. Notice that in the incurred loss tab here, there's no mention of an associated data set. So here, in the final forecast, under the incurred losses, the incurred loss, the difference between the ultimate and the final incurred losses, final of the incurred losses is called ultimate minus incurred to date. So it's not comparable to the outstanding, which is the number you get in the corresponding place from the paid loss triangles. So now when we aggregate, we don't have anything in this column at all. But we do have ultimates because all of the models give rise to ultimates. So in this case, well, the general philosophy is tables are only added together if they belong under the same rubric. If the tables in the individual models have different rubrics, then the corresponding aggregates aren't computed. But this only occurs when we're using a mixture of paid losses, say, and incurred losses, because incurred losses are treated very specially in LRT. We don't try to save you from all the mistakes you can make. So if, for example, you have a composite data set where you mix counts and dollars, you have some NCR triangles and some paid loss triangles, the LRT will simply treat all of them as if they were paid losses. It will call this particular column outstanding. In all of those cases, it will add them together quite happily. It won't check to see whether some are counts and some are dollars. It only does this checking in the case where one of the triangles is an incurred loss, and that's because since incurred losses are used a lot in modeling, we treat them rather specially, and we take account of the fact that incurred losses can't produce calendar year, sum,